But that phenomenon, that aperiodic beating, it is an arrhythmia, but it's not the most dangerous arrhythmia. The most dangerous arrhythmia, and the one that's lethal, is ventricular fibrillation. And what is ventricular fibrillation, usually referred to as VF? Well, let me show you a movie of VF in an animal heart recorded by our colleague T.J. Wu in Taiwan. This is a voltage-sensitive dye recording. So the dye is recording the voltage underneath it. So you're seeing the voltage of the cells. And the red is cell is activating, and then it fades back to blue for the cell is resting. And what you see is pretty disorganized. At first, the waves were coming in from the left, and then they weren't, and then they're going in all sorts of directions. And this is what fibrillation is. Now, as complicated as this spatiotemporal quivering heart mass is, and it's very complicated, nevertheless, there is a relatively simple function that can be computed from heart data. And what it is kind of exactly what you think it would be. We're going to put recovery time here, and for different recovery time, short recovery time, medium recovery time, long recovery time, we're going to put the strength of the following beat. So if the recovery time is nice and long, we're going to get a full strength beat. Let's say this is full strength right there. And that's going to be true for long recovery times. Let's put that in a different color. Now, however, as the recovery time gets shorter, the strength of the following beat is going to get shorter. And this is going to be a curve. And it's going to rise and saturate. But it's reflecting the fact that a short recovery time produces only a stunted or a fraction of a true beat. Now, our mathematical analysis told us that the engine of instability here, as you will not be surprised to hear, the engine of the instability is the slope of this curve. And the slope of that curve is the determinant of the kind of dynamics that you are going to see. In particular, if the slope is greater than 1, and this is now going back to our whole discussion about discrete time dynamical systems, if the slope is greater than 1, it's going to be unstable, and it's going to produce irregular beating. And if the slope is less than 1, it should produce stable beating. So we're able to measure this curve in the heart, and then we looked for a drug. But before we looked for a drug, we did an experiment in the computer. So what you see here is our computer model of the heart. It has about 8 million cells and about 6 variables per cell. And so that's going to be about a 50 million variable ordinary differential equation solved by Euler's method. And what you are going to see is that we did a bunch of experiments in this cube of tissue where we were able to change parameters in the model, and by just typing them into the computer, we were changing parameters to change the slope of that curve. And we got this result, which was sort of interesting, that when the slope was steep on the left, you see irregular wave propagation. You see chaos. On the right, where the slope is shallow, the tissue did not go into irregular beating. There was a single circulating wave established permanently in the tissue, and it beat completely regularly. So we thought, well, wouldn't it be nice if we could find a real drug that did that? And our colleague T.J. Wu did. It's a fast-acting calcium channel blocker. We won't go into the details of the mechanism there. But the bottom line, as you see in the figure, the bottom line is this drug lowered the slope of that curve. So now we have an intervention, and we're going to use it. So on the left, you see again the fibrillation in the heart. You see how irregular it is. Doesn't seem to be following much of a pattern. As we begin to infuse this drug, which lowers the slope of the curve, the heart is converted from irregular to the same spiral wave, the same single periodic recirculating wave that we saw in the computer simulation. We can now see in the animal heart after we lower the slope of this curve. So that gives us an encouraging sign that even in as complex a phenomenon as the heart in fibrillation, there really is a single parameter that can be manipulated to take that heart out of fibrillation. And any drug that does that will have that effect. And it's just a question, which is what we're pursuing now, of how to find a safe drug that lowers the slope of that curve and doesn't have any other side effects. That's going to be an effective drug against fibrillation.